Hello mathematicians, welcome back to another video, linear functions yet again. And if you want to learn more about linear functions, then make sure to check out the link at the top of the description as well as the info box. That's the link to the playlist. There you can find everything regarding linear functions that you are ever going to need during your school life. So check it out and you are going to be really well prepared for your exams. Today we would like to get back to positional relationships. Namely, we want to take a look at the first case we have discussed. When are two or more linear functions in a coordinate system parallel to each other? Meaning, what is the condition such that two linear functions or more never meet, never cross in a coordinate system? We are going to derive the condition for this to hold using an example calculation. And yeah, basically you just need to apply what we find out today, this condition, to your exercises, and then you are basically done. So let us dive right in. So at first we are going to take a look at an example. Let's say we have a coordinate system given and we are going to have a linear function which is going to go through -1 and 2 in some way, okay? Here on the y and on the x-axis. We are going to call this function f because I'm very creative, and we are going to reconstruct it in a second. Now the exercise could say, okay, give me a linear function which is going to be parallel to f. Let's say we need to sketch a function g into here which is parallel to our f. How can we do this? Let us recall what the definition of parallel actually is. So just as a little example, we have this line f, for example, given, and this line. Those two ain't parallel because, well, they are intersecting each other. By definition, they are not parallel. But what does it mean for two or more linear functions to be parallel? Well, they never meet. Meaning, if we were to draw another function into here, what parallel simply means is that each and every point here is the same distance apart from each other. So if we were to take a look at those 2 points, the distance of those two is, let's say, 2 centimeters, and if you were to drag this arrow up, this distance right here is also going to be 2 centimeters apart, as well as this distance, and so on, up until infinity. Each and every pair of points is the same distance apart here on those 2 lines. Now, we could turn this idea around the tiny little bit and let's say, okay, we are going to take this arrow and we are going to put it vertical to our, so in a 90 degrees angle, orthogonal basically, to our chalkboard right here, meaning we are going to draw an arrow which is going to go upwards like this in the vertical direction. Now let's say, since this is a bit longer, this arrow, let's say those 2 points are 3 centimeters apart. Okay, meaning by the definition of parallel, if we were to drag this arrow up here, then those 2 points are also 3 centimeters apart, and so on, up until infinity, each and every pair of points here. We are going to make use of this idea by saying, okay, we can construct ourselves a parallel linear function, okay, parallel to f, if we just drag our function f up here in some way. Let's say by 1 unit. Okay, so we are going to say from the y-intercept we are going to go 1 unit up. Okay, -1 plus 1 is going to land us at 0. Also, we are going to repeat this process. We are going to take this arrow and we are going to put it up here. Meaning from, okay, y is equal to 0 here, we are going to go upwards to y being equal to 1. Okay, so I hope you get the idea. What we did here with the arrows is going to be applied to here. We are going to drag this arrow up here, meaning those 2 points, those 2 pair of points are going to be 1 unit apart from each other in the y direction. Meaning we can connect points now. We have 2 points given, leaving us with a linear function g, which look like this. And now we are going to go ahead and reconstruct our equation. So f is, I mean, both are pretty easy to reconstruct actually. So f is of the form ax plus b, just because it's not a proportional function obviously, because it doesn't go through the origin. It's of the form ax plus b. But there's one thing already given in our graph that we can simply plug into here, namely our y-intercept. We are going to cross our y-axis on -1, meaning our b is going to be replaced by -1. Now what about our a? Now we have to think a tiny little bit. The easiest way to approach this is by using slope triangles. Meaning we are going to put a slope triangle into here. Now we are going to find out what the distance in x and y direction actually are. Okay, so we are going to go from x being equal to 0 to x being equal to 2. So delta x is actually nothing but 2. Now what about our y direction? Delta y is going to go from -1 to 0, so distance is 1. Also, it does make sense that our slope is actually increasing, so we have a positive slope because our function overall is increasing, so we don't get a negative sign, just for the record. So what is our a exactly? Our a now is the y direction divided by the x direction, so difference in y divided by difference in x. Going to give us, okay, 1 over 2 is nothing but 1/2, meaning our f overall is hence nothing but 1/2 times x minus 1. Now what about g of x? We are going to reconstruct our g of x. Okay, it's a proportional function, which is good, meaning it doesn't have a y-intercept, so it's of the form a times x. Now a can be found out by simply reproducing our slope triangle. We are going to travel a certain x direction and then a y direction. So what's the x direction exactly? We are going to go from 0 to 2. That's curious. Delta x is nothing but 2. What about the y direction? We are going to go from 0 to 1. Oh, delta y is nothing but 1. Meaning overall our a is once again 1/2. And this basically settles it, to be honest. Now we are going to find out the condition when two or more linear functions are parallel. We are just going to see which of the parameters here, of our coefficients for example, are equal. And this is going to give us the certain condition. So what about the y-intercept? I mean, here's 0 and here's -1, so this really doesn't help us. But there's one thing which is really magnificent, namely that our slope is the same on both. Both have a slope of 1/2, and this is exactly the condition we were looking for. Two linear functions are parallel if their slopes are exactly equal. 1/2 and 1/2. This is all you have to do. Given two or more linear functions, you want to see if any of those are parallel, then just check if our a, our coefficient in front of the x, is equal, and then we are done. So meaning if we have, for example, those two given, okay, this one and this one, you just need to check if this slope right here of -1/3, for example, is the same as this slope up here, -1/3, for example. And if those two are equal, then those two are parallel. And that basically settles everything. I hope you enjoyed this video. If you did, please like, subscribe, recommend channel if you like. Don't forget to recommend the channel to your neighbors, your teacher, your fellow students, etc. And up until next video, don't forget to check out STEM Merge, etc. I'm wishing you guys a flammable day. Ciao!